Hey everyone, I'm Grayson, and yes, I am back from my recent trip to Wyoming. For those of you that don't know, I spent the last several weeks in Wyoming with friend of the channel, Dr. Dino. Not that Dr. Dino, not Kent Hovind, the other Dr. Dino that's been on this channel before doing debates, and he arranged an expedition to go and find some dinosaur fossils in Wyoming. When I heard of that, I asked him if I could come with, and he was gracious enough to say yes. So we spent the last several weeks finding dinosaur fossils in Wyoming. It was like a childhood dream come true for me. And we will be putting out a video about that adventure and the dinosaurs that we found out there. Expect that on my channel coming up here. And I wanted to say I am at a little bit of a disadvantage in this debate tonight. In that I did spend the last several weeks on the road, didn't really have time to exactly hammer out this exact presentation. And I put out a video on this topic a couple months ago before I left, basically outlining my entire argument for what I find to be the best evidence for the Big Bang. So that's been out for like a month. I think T-Rock has seen it. He's had a chance, like a month, to look at my arguments, research them, and see if he can refute them tonight. So I'm at a little bit of a disadvantage that my opponent knows what my arguments are going to be. He's had time to study them. And I just got back from the road a couple days ago. And in that time, I've spent the vast majority of my free time since playing the new Elden Ring DLC. So I'm a little bit underprepared than I normally am, but I do have a couple slides, and I have taken a course in like a graduate level course in cosmology before. And, you know, I say I'm at a disadvantage, but at the end of the day, my side's the one with all the evidence. So we'll see. I think I'm still at quite a bit of an evidentiary advantage. So we'll see how I manage.
Well, there we go. I appreciate the confidence. And you've probably got, well, firstly, the game on the brain and also dinosaurs, fossils in your adventure. So for those that want to see the upcoming video that you'll be releasing on your trip there, here is your channel, Critical Base Theory, for people to check out. And on your channel, they can find past debates, videos, including your video on the Big Bang Theory, which I'm sure T-Rock has gone over extensively, and this is going to be a good debate. I'm excited. So Grayson, appreciate the introduction. T-Rock, good to have you back as well. It's also not your first time here on the Standing for Truth debate platform. You and Grayson have both had just a ton of debates, numerous debates, so you're both experienced, and so because of that, I'm even more excited for this. So T-Rock, how have you been? And also tell us a little bit about yourself.
Good evening, everybody. Thank you. Thank you, Donnie. Thank you, Tom, for hosting and putting this together. Grayson, thanks for being gracious enough to take this under your very hectic schedule. Congratulations on getting to do some really cool field work. That's really nice. Grayson did make I will say, props to Grayson. He made a pretty quality presentation in his video. Yes, I did go check it out. I replayed it a couple times and tried to kind of follow very specific points in the video. It was a good presentation. Do I agree with it? Obviously not, but it was a good presentation, and Grayson did willfully give up the so-called advantage by giving me his argument up front. Having said that, I'm always at a disadvantage because I have neither the time nor the resources to put together such beautiful presentations. So I have to kind of do it more based on, information content and, kind of verbal and textual presentation. I'm okay with that, though, because I don't want graphics to get in the way of making a valid argument. So anyway, yeah, I'm looking forward to this and appreciate all the time and energy everybody's put into it. So I am ready to roll.
Awesome. T-Rock, thank you for that introduction. You don't have a channel, but you do have a playlist of past debates. So for people who want to see more from you, they can check out that link and watch your previous debates. And so, okay, lastly, our award-winning co-mod, Praise I Am. Good to have you here. I appreciate the time, brother. Praise, how you doing tonight? Are you excited for this?
Yeah, it's a pleasure to be here. I love both T-Rock and watching Grayson and their debates. Two game debaters, and it should be a good one. I'll just be here to guide along the discussion if any errors, unforeseen errors come up, and I'll just try to keep it going. It's a pleasure to be here, though.
I appreciate it, Praise. Yes, Grayson and T-Rock always make for a memorable, engaging debate. Both are very knowledgeable. So let's get right into this then. We are going to be having, it's kind of a mix of formal and informal in the sense that we're going to have an opening statement. We're going to give Grayson the first opening statement, whatever time he takes, not really strict on the time. Go through your arguments, and we'll give T-Rock roughly equal time. Then we're just going to jump into a discussion. So we'll have some arguments and points on the table for us to go back and forth for a while. And then when we've exhausted the topic and Grayson and T-Rock are bored of each other, we are going to get the audience involved. We're going to interact and engage with your questions, your comments, your objections. So please, if you do have a question or a challenge on tonight's topic, is the Big Bang a reasonable scientific theory? Please let me know who the question's for, and then do your best to tag me either at Standing for Truth or at Donnie or at Praise the IM. We'll both be saving questions tonight. Okay, Grayson, we're going to hand it over to you. And whenever you'd like me to get your slides up, just let me know.
Cool. Yeah, we can put up the slides now. You can see my title screen there, as well as you can still see me. I'm not blanked out or anything.
No, looks good. You're on the screen and your slides too.
Okay, cool. Then basically, as you can see on the screen, we're going to be talking about the Big Bang and how it's, first of all, we're just got to get a few things clarified. It's not an explosion. I want to be very upfront about that and just correct some of the common misconceptions that I see people having about the Big Bang. And Donnie or Praise, could you clarify really quick, is the exact topic of this debate that we settled on, is the Big Bang a reasonable scientific theory?
Yes, that's right.
Okay. So yes, I will be answering that question with this debate. Obviously, I'm going to be answering it with a resounding yes. So let's get into that. First of all, I just want to show this is an explosion. You can see it starts from an individual center point, and then it expands outward from that point in all directions. It imparts like linear and rotational momentum as it's expanding. We know what an explosion is. It's a like kinematic process. That's in contrast with an expansion. You see on the left, each and every square is getting larger. It's doubling in size. Each and every square in this grid is expanding, and all the things in those squares are getting farther away from each other as part of this expansion. This is obviously not an explosion. This is an expansion of the space in between all these objects. This is more akin to what the Big Bang is. Not an explosion, but an expansion. So the actual Big Bang model tells us that the universe was once in a smaller, hotter, denser state. That's the elevator pitch for what the Big Bang is all about. So the evidence that I'll be talking about tonight is evidence showing that the universe was once in a smaller, hotter, denser state. Just to clarify some other misconceptions and just get ahead of some of the questions that I'm sure that we will inevitably get. Without new physics, like physics of quantum gravity or like some new understanding, some grand unified theory that we don't have in physics at the moment, we cannot know about the very, very earliest moments of the universe or what happened before that. If there even was one, if it before even makes sense to ask, because this might have been where time came from. We don't know. So again, there's a certain point when we use our frameworks of physics to trace back for what the universe would have been like as it gets smaller and smaller and smaller and denser, we can have the physics that can tell us what those dynamics would be like up to a point. And once we reach that point, the current physics that we have ceases to give us accurate descriptions of what is actually going on at those incredibly hot and dense moments where the actual fundamental forces are getting confused for each other, and it gets really, really complicated really fast. We don't have the physics to say and give an answer for these questions of, well, what happened before the Big Bang? Or what was the very first instant? Or where did this come from? Like a lot of the people's basic questions, we just don't have the physics currently to answer. Like the most honest answer is that we don't have the evidence to say one way or the other. So I'm not coming out here tonight saying, look, Science has all the answers to all of your questions. We know everything and everything is solved. Okay, that's not obviously the current state of science. So there will be times tonight, I'm sure, well, where I will be asked questions that there is no honest answer to give based on the evidence, because the evidence is not there for some of these more underlying questions. However, and this is a big however, there is sufficient evidence there today to show definitively, beyond a shadow of reasonable doubt, that the Big Bang did happen and that the universe was once in a smaller, hotter, denser state, so small and hot and dense that, everything was essentially condensed down to plasma. And we will talk about the evidence for that. The last thing I want to clarify is that the Big Bang model does not say that the universe came from nothing. A lot of the times people will throw this and say, oh, you think something came from nothing, or you think a dot of nothing exploded. This is a straw man of the Big Bang. The Big Bang does not claim that first you have nothing and then you have a singularity that just explodes into everything. That is absolutely not what is being described in the Big Bang model. So I wanted to just clarify those points up front. So what about the actual evidence? So what you're looking at here is a graph of the very first evidence that kind of got people to accepting that this Big Bang model did happen. And this didn't convince everybody. There were still some prominent physicists and cosmologists who were, Big Bang detractors at this point in time in the early 20th century when this data first came out. But this convinced a lot of the experts in the field, including Einstein. So let's just break this down really quick. This is called Hubble's flow or Hubble's law. It's just showing that when you look out at very distant galaxies, you see that the farther and farther away that these galaxies are, and you can determine this by various cosmological distance ladders, like certain standard candles of supernova and things. The farther away these galaxies are, the more red-shifted they appear. And things are red-shifted when they're moving away from us, blue-shifted when they're moving towards us. So it seems like there's this very distinct relationship where the farther away a galaxy is, the more red-shifted it is. And this was enough to convince a majority of experts in the field that the universe is expanding, that these galaxies are all getting farther and farther away from us the farther they are, as in the space in between us is getting larger. So this is showing the expansion of the universe. This is Hubble's flow. It was the first piece of evidence. But I would argue that there's an even stronger piece of evidence than this. Let's look at the very furthest galaxies, because this is something that we're finding out more about in modern times. Just in the last couple years, like James Webb Space Telescope has shown us a lot of information about the very, very farthest galaxies. Here are some properties that they have that, again, if you say that the Big Bang did not happen, you have to explain why the farthest galaxies are like this, because these are all predicted by the Big Bang, all these properties that we observe. But the alternative, like the Dr. Lyell's of the creationist alternative to the Big Bang, would say that the very farthest galaxies they predicted were essentially like our own. But when we actually look at them, we see that, one, they have the highest redshift. No big surprise. That's just Hubble's law. They have very low metallicity, which means they have very low amounts of the heavier elements. Like their actual elemental composition is different than the galaxies closer to us. And this is exactly in line with what the Big Bang predicted, where the amount of heavier elements in the universe goes up over time. So in the past, the very earliest galaxies would have very low amounts of heavy elements. That's exactly what we're seeing with James Webb. Number 3, this is a huge one. This is something I've never even seen any Big Bang skeptic ever try to explain. These very farthest galaxies are time dilated. That means that when we watch them, we literally are watching them in slow motion. Okay, so something is causing that. The Big Bang is pretty clear. The Big Bang model is that space-time expanding, the expansion of the universe, is a direct cause for this time dilation effect. It is explaining exactly why, if these redshifted galaxies are so redshifted because of the expansion of the universe, we would expect to see them in slow motion due to relativistic effects with space-time expansion. And that's exactly what we see. Like when we look at the farthest distance galaxies, they are literally in slow motion. That's got to have an explanation. If you reject that the universe is expanding, explain that one. I'd love to see it. I'll just move through these pretty quick. They're located inside ionized bubbles of gas. This is super weird if you don't believe in a Big Bang. But again, the Big Bang model explicitly predicted this. Like after you have the Big Bang, before any of the stars and galaxies have formed, everything is just a non-ionized molecular gas of hydrogen and helium. Then once this condenses into stars and galaxies, it starts through the solar radiation. It starts literally ionizing all of this gas in a bubble, an expanding bubble around it as the universe expands. And we literally see these bubbles with the James Webb Space Telescope. So again, another confirmed prediction of the Big Bang model. James Webb has made a lot of these. Again, just really quick, these furthest distance galaxies are like really, really weird. They're super small, super massive, very, very bright. They're really odd shapes like fuzzballs and pears and things. And they have really, really high amounts of stars being produced inside of them. This is what we might expect when the universe is much, much denser than today. But for today's universe, for today's galaxies, absolutely not. And if you reject the Big Bang, which explains all of these points, it explains all of our observations of these furthest away galaxies, you need to explain these points with your alternative of the Big Bang, because it's pretty impressive explanatory power. But I mentioned there's a strongest line of evidence. This is the one that this is my main line of evidence, what I consider to be the strongest line of evidence for the Big Bang. My main argument tonight, the cosmic microwave background. So just really, really quick, in every single direction that you look in the night sky, you see this background. Every single direction, you can detect microwave radiation coming from all directions at once. It's remarkably uniform. It only varies about 1 part in 100,000. It's all around the same temperature. And you can see the tiny, tiny little micro fluctuations are represented here in this image. So this image is actually kind of like how they take a globe and they make it into a 2D projection. This is a 2-dimensional projection of the 3-dimensional shape that basically is in the entire night sky for the whole Earth. So you could imagine that this is wrapping around the Earth like a shell around it. And this is the pattern that we see in what's called the CMB here. And so this microwave radiation is pretty much a nail in the coffin for the Big Bang. To my understanding, there is not any alternate explanation for what this CMB even is other than from the Big Bang. So in the Big Bang model, right, I said the universe was smaller and hotter and denser in the past. And when you get so small and hot and dense, you just taken everything and you just mash it all together. That energy density gets so high that it turns into a plasma. And this is known physics. We have generated plasmas. We know that this is how it happens, right? So as this universe is expanding, at some point, it's just all plasma. And when it expands and cools to a large enough size, that plasma can then cool down and combine back into atoms, right? We've also seen this process in particle accelerators, nuclear fusion reactors. We've seen plasma condense back into matter. And when it does that, it releases light. It releases a photon of radiation. And this is what we're viewing when we see the CMB. We're seeing at one point when the universe went through a phase transition from being small and dense plasma to expanding and cooling and forming atoms, it released a lot of light. And that light has been traveling since that period of time until it hits our detectors today. It can kind of be a little bit of a mind-blowing thing to think about. But if we want maybe clarification, maybe we can do that in the Q&A later. But this is like the oldest light source in the universe. It's like the most perfect black body radiation source in the universe. This is what it looks like when we actually detect it. The thing in the bottom right here is the satellite that was actually in orbit measuring all of this. And it's not just, this is the main point I want to make here. I don't want to get lost in the details here, but it's not just the existence of this cosmic microwave background that is such strong evidence for the Big Bang. It's actually the pattern here. It might look like there's no pattern here between the red and the blues, the hot and the cold temperature variations, but there actually is. You can use an advanced type of mathematics to break this down into its components, right? kind of like how they take really complex wave patterns and break them down into simple sine waves. You can do that for this kind of three-dimensional sphere. And when you do that, this is what you get. Okay, you can kind of see here that there's different like modes of how they're broken down, where you can see there's these L values, and each L value makes it more and more detailed. And you can see here, this is a plot of all the L values on the x-axis and the temperature fluctuations on the y-axis. And I don't really like getting in this level of fine details for a debate opening like this, but this really is like in my opinion, the strongest evidence is this graph right here. Like, if you understand this graph, I don't think that you could possibly argue that the Big Bang did not happen. I mean, we will see tonight, but just this is the gold standard of science. You use your hypothesis, you generate a prediction, you test your prediction, and you compare the results. And this is a confirmed prediction. So just to show what you're looking at, this little green line here that you see, that is the theoretical prediction for what this pattern should be. And remember, we're looking at the patterns written into this cosmic microwave background. It looks totally random, but again, you can use math to decompose it into this graph right here that has this set shape. And you can see that the theoretical prediction almost perfectly matches each one of these red dots is the actual measurement. You can see, like, it is just beyond any kind of coincidence that you could fathom, that you could have the data perfectly match the theoretical prediction. I mean, if the Big Bang did not happen, this absolutely needs to be explained, because, right, like I said, I mean, this is the golden standard of science. You make a testable, falsifiable prediction, and it matched perfectly with the data. So I think it's pretty obvious that the Big Bang is obviously a reasonable scientific theory if it is making predictions that have been tested and shown to be so perfectly accurately matched. And you could not generate this theoretical prediction without a Big Bang model. Like, some of the underlying components to this graph that go into making this theoretical prediction are things like the age of the universe, things like the different cosmological parameters, dark energy, dark matter, inflation. Like, it's all encoded into this theoretical prediction that matches so perfectly with the actual reality of the measured data. So this is what needs to be explained for anybody that rejects the Big Bang. How is it that we can use the Big Bang model to generate such an insanely precise and accurate prediction that perfectly matches real world data? Thank you.
Grayson, thank you very much for that opening presentation and the visuals as well. Very helpful. So let me reset the timer. That was 16 minutes. So T-Rock, we will give you equal time. Actually, I should let the audience know that I am all caught up on your questions. I appreciate how engaged everybody is on this topic. It's certainly an interesting one, that's for sure. And so I do have all your questions so far that have come in saved. Okay, T-Rock, whenever you're ready, you have 16 minutes. And if you need your screen shared, just let me know. We can do that as well. And oh, I see it here.
Right. Let me know when you can see it.
Yep.
Yes, looks good, T-Rock. So you're good to go. I'll start the timer on your first word again. You got about 16 minutes.
Okay, thank you. Topic of the debate is the Big Bang a reasonable theory? Of course, I take the position that no, it is not. I'm going to real quick review a few things. What is a theory? It's well accepted. It's supported by rigorous testing and observation. It fits the data. It's based on natural causes, and it's falsifiable. The components of the Big Bang cosmology are roughly this: quantum fluctuation, inflation, deflation, cosmological constant, and then I've got in parentheses for a reason, dark energy and dark matter. Okay, so the timelines look kind of like this. Gravitational constant, as in the universal gravitational constant from which we derive, for example, the gravitational attraction that the Earth provides us, was first calculated in 1797. General relativity was first described in 1915. The cosmological constant, which, by the way, was comes from Einstein, I'm pretty sure, but anyway, it was 1917. And the Big Bang was proposed in 1927 for the first time. The Hubble constant was first measured and described in 1929. Dark matter was proposed in 1933, hence why it's in parentheses. It is actually not part of the original Big Bang proposal. The CMB was discovered in 1964. This is hailed as the successful prediction of the Big Bang model. And then there's dark energy, was first described in 1997, very late coming in the game. And we'll talk about why that is in just a minute. What is not a theory? Supernatural. If something relies on the supernatural, it cannot fit a quote-unquote scientific theory. If it's not testable, it cannot be a scientific theory. If it's not falsifiable, it cannot be a scientific theory. If there are too many assumptions, it should not be a scientific theory. It technically cannot be, but we will find out that people will do this anyway with so-called theories. Okay, I want to point out a couple things real quick. Grayson indicated that the Big Bang was not an explosion. I don't have any issue with that whatsoever. The word theory here does have a specific meaning in science, which is a very frequent, common complaint by Big Bang proponents and evolutionists and deep timers and so forth. And that is that sometimes they might hear a creationist say something like it's just a theory. What I really want to point out is this is really just semantics. If you go watch, listen, read any of the available content from professional scientists, they use these words in the exact same way the creationists do. If you understand it in context, it's not a problem. In other words, the argument itself that you're using the word wrong it's just a bogus waste of time. If you understand the concept, then the context of the statements being made, you can very well understand whether you're using the word theory in the formal scientific sense or whether you're using it in more of a layman street kind of sense. And yes, professional scientists absolutely use this word in the layman street common vernacular sense, not necessarily altogether in the strict scientific sense. Okay, having said that, components of the Big Bang cosmology, quantum fluctuation. It is supernatural and it is not testable. Why am I saying it's supernatural? Because nobody's ever observed such a quantum fluctuation as is required to produce this alleged Big Bang. It's supernatural, meaning literally above nature. It's not something that happens in nature. It's not something anybody has ever seen on any scale. A quantum fluctuation cannot produce a flash of light or a puff of smoke, let alone an entire universe with planets and stars and galaxies and all the structure that goes with it and the organization that's in it. The quantum fluctuation itself that the Big Bang rests on is just a made-up idea outside of nature, and it's not testable. There is no way to produce any remote semblance of a quantum fluctuation in a laboratory. It would actually be very antithetical to the theory of the Big Bang if it were. Inflation, another supernatural, not testable idea that is thrown at the Big Bang to make it seem plausible. The rapid expansion of space, nobody's ever seen such a thing. Nobody can demonstrate such a thing. It's outside of nature. It's not something that happens naturally. The space doesn't, what inflation actually implies, oddly enough, is it kind of implies that, okay, the space between 2 points is increasing. But when you say it's not an explosion, it's a rapid expansion of space. Instead, it kind of implies that the objects have no kinetic energy from their original state, no additional kinetic energy. That means whatever the objects were doing before this inflation happened, they pretty much have to be doing the exact same thing during and after inflation, because they're technically not moving. Space is just filling in between them and making greater distances between them. Oddly enough, if you think about that very long, you might think an explosion in the conventional sense might actually be a better explanation than inflation. It's not, and I'm not claiming it is. It's just that inflation, again, it's just a made-up idea. Deflation. At some point, this inflating universe supposedly slows down under the influence of gravity, nonetheless. Deflation, because inflation is above and outside natural cause and effect. Deflation is as well, and it's not testable. There's no way to demonstrate that you can suddenly make rapidly expanding space at orders of magnitude faster than the speed of light suddenly just slow down and come to a halt or whatever. The cosmological constant, it's an assumption. It's essentially a free parameter. Cosmological constant came from Einstein back at a time, this was pre-Big Bang, but back at a time before it was understood that the universe is expanding. There's some particular phrases that describe Einstein's version of it that are quite telling. But the bottom line is, in Einstein's day, when he first came up with this cosmological constant, what the consensus at the time was that the universe was more or less in a static state. It wasn't moving. And Einstein wasn't inclined to argue against that. So he basically came up with this cosmological constant to fix what appeared to be an issue with galactic rotation and some other observed physics in deep space. Okay, dark energy, also not observable. It's an ad hoc free parameter, which we'll find out. Dark energy and the cosmological constant are very closely tied together. And so it's not that they're exactly the same thing, but they're, for all intent and purpose, interchangeable. Dark matter, not observable. It's an ad hoc free parameter. And it's specifically to describe rapidly rotating galaxies. It's kind of like the new fix that Einstein was originally trying to implement to explain physical motion in deep space. But it's not observable by definition. It literally is not observable. To some physicists, they would say that it is matter that does not interact with light. In other words, if you had it in a jar in the lab, you couldn't see it because it won't interact with light. Light won't reflect off of it. It would have no color. It would literally be invisible to the eye, although hypothetically you're supposed to be able to detect its presence in some way or another. Okay. Cosmological constant, aka lambda, that's the capital version of lambda, the symbol you see there. That's what's frequently used to refer to the cosmological constant. Just a few phrases here that kind of describe what we're talking about. It describes the energy density of empty space. It is called the worst prediction in the history of physics, and it's called Einstein's biggest blunder. And I think Einstein himself actually called it his biggest blunder. It has been a thorn in the sides of physicists for decades. It still presents a challenge for models designed to explain the expansion of the universe. Lambda's theoretical value, obtained through quantum field theory, is nowhere near the value obtained from the study of type 1 supernova and the CMB, interestingly enough. In fact, it diverges by as much as 10 to the 121st power. That's more than there are atoms in the observable universe by a long, long shot. In other words, lambda is entirely made up, and how it is used doesn't even fit the CMB model anyway when it comes to trying to explain Big Bang cosmology. So continuation, it is therefore of little wonder that cosmologists are eager to tackle this disparity. These are quotes, by the way. The reference is given here at the bottom of the screen. It's a article titled "A New Generation Takes on the Cosmological Constant." The cosmological constant, in one form or another, is a century-old puzzle. It is one of the biggest problems in modern physics, says theoretical physicist Lucas Lombreiser from University of Geneva, Switzerland. Moreover, the cosmological constant is the most dominant component in our universe. It makes up 70% of the current energy budget. How could one not want to figure out what it really is? Now, I didn't emphasize that word really here, although I kind of should have, but I'm just presenting it exactly as it is in the original text of this article. But can the field accept these revolutionary ideas, or has lambda become a comfortably familiar burden? It's a burden. What Grayson is defending is called the lambda CDM, cold dark matter model. And so what he's defending is this cosmological constant to describe lambda, in other words, dark energy, and cold dark matter, which is otherwise just known as dark matter. Okay, so on dark matter, it doesn't interact with light. It's used to explain the unusual rapid rotation of galaxies and rapid movement of galaxy clusters. It represents a correction to relativity plus gravity in large scales. It is not needed, for example, right here in our solar system. In our solar system, you would have something like, for example, the trajectory of Mercury is you can make a rough, decent estimation of its trajectory using basic Newtonian physics with gravity, but you get a much better, more accurate rendition of it using gravity plus relativity. But out in deep space at large scales, even the corrections from relativity don't work anymore. So not all physicists think it is a viable solution. Currently, dark matter, that's referring to dark matter specifically, currently competing with MOND and MOG. MOND is modified Newtonian dynamics, and MOG is modified gravity. They're two competing ideas that are basically meant to try to replace dark matter. And that's coming from the current scientific crowd. They're basically looking for alternate solutions, because dark matter does not seem to be well, it's got major problems in the fact that you can't see it, you can't detect it, and some of the observations that are tried to, some of the data that's tried to be compiled to demonstrate that there is indeed dark matter in the outer fringes of some of these galaxies. Some of the observational data doesn't match it very well at all, and hence the need to come up with some other idea. So, but it is currently the most widely accepted solution to the disparity in the motion of galaxies. Okay, here's some resources. We won't go through a whole lot of this, but this is a lot of what I spent my time on, listening to professional physicists talk about some of this stuff. And I'll just suffice it to say that the titles of these videos in and of themselves tell a pretty bleak story, and you can watch the actual video. The link's provided there. If you're able to capture that off the screen, you can go check some of these out, or just look them up by the title, and the name of the channel is what these actually are. It's individuals' names, but that is the name of their channel. Anyway, Modified Gravity Strikes Back by Sabine Hossenfelder. In other words, it's some data has been compiled.
T-Rock, you got 1 minute left. 1 minute. Sounds
good. Thank you. In other words, modified gravity does have some data compiled to make it look like it could potentially replace dark matter. Astrophysicists keep finding things that shouldn't exist. I think I know why. Sabine Hossenfelder. What are these? Bizarre JWST discovery breaks galactic models again. Anton Petrov. Bad news for dark matter. The data doesn't fit at all. Sabine Hossenfelder. Modified gravity strikes back. Sabine Hossenfelder. JWST rules out most likely culprit for the crisis in cosmology. We really need to talk about that crisis in cosmology. That's from Dr. Becky. What is the biggest flaw in the Big Bang Theory? Dr. Paul M. Sutter. What if singularities do not exist? PBS Spacetime. We can kind of talk about some of the ideas that get elicited from this, but I'll close there and we can come back around to some of these ideas.
Okay, thank you very much, T-Rock. Gentlemen, that concludes our very thorough opening statements. Okay, so we got quite a few points and topics on the table related to the Big Bang Theory. Gentlemen, excellent job with your presentations. Thank you for the visuals. Those are always helpful. So what we're going to do is jump right into a discussion. And so we'll hand it over to Grayson. Grayson, feel free to pick a point or topic that you'd like to start off with. Go ahead.
Okay, yeah. I just want to start with 2 quick points. The first one is that, T-Rock, we can talk about all the different things that you brought up, but I just need to point out that none of them are really on topic for the Big Bang. Like I want to differentiate between the Big Bang model and the lambda CDM model. Yes, it's true. Like the lambda CDM model is the current consensus in the field of cosmology, and it contains dark energy and dark matter and inflation and all that. But you can reject dark matter, you can reject dark energy, you can reject inflation, you can reject all of that, and you could still accept the Big Bang model. So there is that little bit of distinction there. Like we can spend this debate talking about dark matter, dark energy, and inflation. I'd love to talk about those things, but they are a little bit off topic to the actual Big Bang model itself, which, as you pointed out, kind of precedes them in time. And the second point, really quick, is that all those sources that you cited at the end there that are like, is there a problem in the Big Bang? Oh, modified gravity, and all those titles of those YouTube videos, each and every one of the people in those YouTube channels, because I watched Sabina Hasselfelder, I watched Anton, I watched PBS Spacetime, all of them accept the Big Bang model as reality. All of them accept that the Big Bang happened. So kind of, you're pulling from these sources that all disagree with you.
Okay. Let me first point out, you want to separate Big Bang theory from lambda cold dark matter, but your 7-minute video literally put that at the front and said, this is the version that I'm describing.
Yes. So I will agree. Like the evidence that I showed, that chart in the final slide of my presentation is incredibly strong evidence for the lambda CDM model. It contains dark matter, dark energy, and all that within it, because obviously we had to account for those things to make an appropriate prediction, because those things exist in reality. And I'm happy to get into any of that. We can talk about dark matter, dark energy. I do think that those things are observable. We send up instruments to observe them, and we can talk about all that. But I needed to make the point that those are all a little bit separate than the idea of the Big Bang itself, which is just that the universe was smaller, hotter, and denser in the past. So maybe we could start by talking about the Big Bang, and then maybe talk about the Big Bang model for a bit, and then talk about dark matter, dark energy, and stuff after that, if you're okay with that for the discussion.
Yeah, that's fine. If you actually go back and rewatch my presentation, I deliberately started out with specifics to the Big Bang. That do not directly point to dark matter, dark energy yet. And
so, well, then let's start with that. I want to first, the first place I want to start with this is, do you acknowledge that the universe in the past was in a smaller, hotter, and denser state?
No.
Okay, so do you acknowledge that the universe is currently expanding?
Yes. And with one minor caveat. I could take it or leave it. I would like to point out that there are creationists that probably reject the expanding universe, but a lot of creationists are fine with it. Personally, I could take it or leave it. I'm fine with it. If we want to say the universe is expanding and we believe we have good observable evidence for that, I'm fine. That's
okay. So I would say that we definitely do. And we could talk about the evidence that the universe is still currently expanding today. But
sure.
I think logically, really quick, logically, if you acknowledge that the universe is currently expanding, as in getting bigger, then that logically necessitates that in the past it was smaller.
Sure, but smaller, hotter, denser state is a little too qualifying.
So the reason why all of those are necessitated by smaller, right? Because you're taking all the stuff in the universe and having it in a smaller amount of space. That means everything is denser, which means everything is hotter. That's just that just logically, physically follows.
That sounds reasonable, except nobody even knows how big the universe is. And therefore you can't know how much you should retract it.
You don't really need to know the current size of the universe in order to like calculate how its density would change as it gets smaller. Like you can estimate the current energy density of the universe today without knowing its size. And you can know that if the universe gets smaller, that energy density will increase. So it follows logically that if the universe is expanding, then it used to be smaller in the past and thus was also hotter and denser. I mean,
Okay,
you're just getting the same amount of material in a smaller amount of space.
Sure, but there's a couple of logical problems with that. First of all, that energy density you're describing is the cosmological constant.
No, it's not.
Yes, actually it is.
I'm talking about the total energy density. So that includes the 70% that is dark energy or the cosmological constant, whatever you want to call it. But that also includes matter, dark matter, all of the energy density of the universe.
Sure, but 70% of the total energy budget means that if you can't explain that part of it, you have no explanation at all.
I reject that logic. I mean, you just because you don't know like what dark energy is, like on an ontological level, you can still account for it in your calculations. You can still measure how much of the universe is made up of this dark energy. This, basically that 70% is a way that you can see it without. If you didn't want to introduce dark energy or cosmological constant or stuff that you might consider to have historical baggage, the way you could think about that is that we have measured that 70% of the universe has some sort of energy dynamics that we don't know about. That could be dark energy, that could be cosmological constant, that could be quintessence, that could be anything. It might not even be any of our current hypotheses for it, but like that 70% is real. That is measured. Like 70% of the universe is something that we don't understand, whatever it is.
I'm not actually directly contesting that, but now you've kind of come full circle and you're defending essentially dark energy, because that is what is the idea that's used to describe that 70%. But you said you didn't need dark energy.
I would say that you don't need dark energy to explain that 70% necessarily. There are different alternatives that are not dark energy. Dark energy is like something specific. This is why people, like when you brought up the idea of the cosmological constant being the worst prediction in physics or whatever, I think that claim kind of falls apart upon closer scrutiny, because when you actually are looking at the mathematics involved of making that prediction, like I have checked it out, and there are like several leaps in logic that like need to occur in order for you to extrapolate, oh, here's the energy density of the vacuum fluctuations, and so now we'll extrapolate that and assume that empty space-time, that vacuum, gravitates. You cannot make that assumption. It could be possible that vacuum fluctuations do not gravitate or have a different gravitational impact that we're not aware of, because again, well, not again, but I wanted to touch on this because you said quantum fluctuations are supernatural, they're not observable. Dude, yes they are. like quantum mechanics is built on our observations of quantum fluctuations. Like the Heisenberg uncertainty principle necessitates the existence of quantum fluctuations. This has been tested and observed to like 9 decimal points of precision.
I think you're making an equivocation fallacy, because the observed fluctuations that are derived through quantum physics are not the same as what's required to produce a Big Bang. They
So
can't be.
differentiate them for me. Tell me what's the difference there. Because are you just saying that because the primordial quantum fluctuations were fluctuations in a field that we haven't properly characterized in quantum field theory, or what are you talking about?
Well, I mean, the most obvious thing is that the whole point of the quantum fluctuation behind the Big Bang is that there is no universe. There is no gravitational constant yet. There is no space. There is no space-time. There's a fluctuation of a quantum energy field, but everything you do today already has everything in place. And it doesn't, like I said before, this quantum fluctuation thing's not scalable in any sense. You can't produce flashes of light. You can't produce puffs of smoke. You can't produce anything from them other than energy signatures where you use literally tens of thousands of tons of matter worth of equipment and tens of millions of kilojoules of energy to produce one tiny little signature. That's antithetical to what the quantum fluctuation of the Big Bang was supposed to be.
Yeah, so I think that there's a bit of straw manning going on here where you're saying that the quantum fluctuation was occurring without space or time. Like, square that circle. That one doesn't make any sense. I think that I don't know where you picked that up, but I don't think that's an accurate understanding of the model. Because how you have fluctuations without space or time? It doesn't make sense.
Real quick, then, you have a graphic, and I'm not sure if it's exactly the same graphic or not, but you had a graphic in your 7-minute video that's very similar, if not the same, to the graphic you presented just a little while ago. And basically, you demonstrate what the Big Bang looks like from beginning to end in a chronological sequence.
Yeah, let me share that. Let me share that so people can see what you're referring to, because I'm pretty sure I know what which graphic you're talking about here. Let me share my screen. This one.
Yeah, right? Can you zoom up? Can you zoom that up a bit? So that we can read the labels on it.
Yeah, there you go. You can see that?
Yeah. So there is a quantum fluctuation.
Yep. Again, you'll see nowhere in this that there's ever a point where, oh, here's space and time introduced, and you see that the quantum fluctuations are not exactly at that 0 point. So there is space and time, because in order to have quantum fluctuations, you need to have a quantum field which must exist in space and time.
Must exist in space and time. So that's kind of an interesting idea, because right after that, or you said it, you're basically pointing to a place in the midst of the inflation graphic there, right? And that's why you're making that particular argument.
The idea is that the initial primordial quantum fluctuations, which again just happen in any quantum field necessitated by the Heisenberg uncertainty principle, you necessarily have to have quantum fluctuations in any kind of quantum field. So these initial quantum fluctuations are exacerbated and blown up by inflation. That's the idea.
Right.
It's not like space and time didn't exist yet.
Clarify something for me real quick, and I'm going to come back to that, because that is a super important point. So we got to come back to that, but I want you to clarify something for me here. Most physicists or Big Bang proponents would say that this quantum fluctuation was quote unquote pure energy, i.e. massless.
Yeah, this would be before massive particles existed. The Higgs field was in a different phase at this point. I think Steven Weinberg worked this out, the physics behind it. Okay. But yes, this would have been a massless phase of the universe.
So this is so now back to the thing I'm calling the super important point that you have to kind of point out here. The Big Bang theory, because we have this apparent expansion, and again, for the sake of argument, I'm just assuming the universe really is expanding, and we can observe all the necessary things that essentially prove that. But the concept of the Big Bang is that you just extrapolate back, shrink space in, and then at some point you're down to a super hot, super dense state, right? Now, the obvious problem with that to me is that you're extrapolating in 3D space, but you don't want to call it a 3D explosion. even though space literally has to space itself. And you say
the reason it's not an explosion is because it doesn't have a center point, right? That's the biggest differentiating factor between it and an explosion. All explosions have a central point or central points where they explode from. The Big Bang does not.
Well, see, that sounds logically the exact opposite. It sounds like it literally, no offense to you or anybody else, that it literally sounds like logical contradiction. You're going to extrapolate three-dimensional space in all directions back to a smaller point. That implies logically that there is a center to it.
I don't think it does, because the issue that you're having here is that you're thinking of the universe itself as a three-dimensional object. But in order for you to think about it that way, your perspective has to be in space outside the universe, which that is the logical contradiction here. But in order for you to think of the universe as a three-dimensional object, you have to be outside of it. So square that circle.
Okay, I will. I'm glad you said that, because I will. Because going back to your 7-minute video, you cited that as to be essentially undeniable proof that that demands a really, really compelling explanation. I'm kind of projecting a little bit here, but I think that's what you're getting at. You need a really compelling explanation if you're going to reject that. Here's the problem. Your video is based on, per the video, it's based on 6 fundamental tenets of physics, right?
Fundamental constants or parameters, yes.
Parameters, 6 fundamental parameters of physics. One of them is 3D space.
Which one of those are you saying is 3D space? Like the Hubble?
Let me share my screen, and I'll show what all 6 of them are.
Okay. Because like there's the Hubble constant, there's the dark matter energy, there's the matter content of the universe, there's the dark energy content of the universe. That's 3 of them right there. There's a lot of ones that are a little bit more subtle to explain, like the A sub S, the amplitude constant. Like there's a few weird ones out there, but I don't think any of them just corresponds to space itself.
Can you see my screen?
Yes. Yeah, it's up.
I'm gonna blow this up so everybody can see this. These are the 6 parameters that are used to make that argument that you're making. It's the density parameter, the gravity constant, it's the universal gravitational constant, which is Newtonian, 3 dimensions of space, Q, the part in 100,000 ratio between the rest mass energy of matter and the force of gravity, the measure of nuclear efficiency, epsilon, and the cosmological constant, lambda. Those are the 6 deals. But on the one hand, you're saying that everything we see in 3D space is explained by the Big Bang. In your presentation, in your video presentation, you say that graph is based on these 6 parameters, but now you're saying you can't think of it in terms of 3 dimensions.
Yeah, so I think that what you're doing here is sort of reducing these parameters to the point where it's kind of no longer accurate. Like, I think what you mean by the 3 dimensions parameter here is you're talking about the spatial curvature of the universe.
No,
but
there is
okay, then you're just mistaken on what the 6 parameters are. Then, like, this is just incorrect. Then,
let me explain what the 3 dimensions is actually about.
Okay.
It does have implications for the curvature of space, yes, but the reason it has to be 3 dimensions and not some other number is because if it were 2 dimensions, you basically can't get anything physical to make sense in our existing universe. If it's 4 dimensions, well, let me see if I can kind of put a finer point on this. If it's 2 dimensions, I believe everything collapses back on itself, and if it's 4 dimensions, any slight change in velocity anywhere in the cosmos, in a solar system, it doesn't matter. If it's 4 dimensions, what happens is everything just flies apart because of the inverse square law. It becomes the inverse cube law, and then everything just flies apart.
Where are you getting this from? Where are you getting this from, T-Rock?
Where am I getting this from?
Because I learned what the 6 parameters were, and they're not matching up to what you're saying.
Let me see if I can find my source here for you.
These are they're called the vanilla 6 parameters in cosmology.
Okay.
Like spatial curvature is one, Hubble's constant is one, the total amount of matter, the total amount of dark energy, like the amplitude, like they're not what you're describing them to be.
So you gave a particular reference in your video presentation, that it was, what was the name of the paper you described? I think I have it here if I can.
I don't have it offhand. I'd have to get that to you at a later date.
I know I've got it here. I just got to point at the right one to make sure that. But it was something about the 6.
The 6 parameters, yeah.
Yeah. So I start my cosmology stuff right here. It's not James Webb.
Well, I'll just tell you that the number of spatial dimensions is not one of the 6 parameters. Yeah, and there's nothing supernatural about these 6 parameters either, or there's nothing non-testable about them. They're all falsifiable and measurable. They
Actually, that's not true either. But anyway, my point was that you provided a particular reference to where you came up with these 6 parameters and how the science was worked out. And so what I did was I took the title that you gave and I just did a quick Google search with the author's name and tried to come up with the same deal. What I came up with, honestly, was kind of a cookie wall, that you had to accept their cookies and so on and so forth, and to be able to view the content. And so I didn't really want to do that. So what I did was basically took some of the other returned search results, and it gave me a different title by a different author, but the same basic topic. And he basically went through those 6 deals, described each one, and explained what their role in the Big Bang model was. And that's where I came up with this idea.
I think that something must have gotten confused along the way, because the 6 that you're saying are not the same as the 6 I'm talking about. So I don't know if we want to rehash this whole thing right now, but I'm just telling you, like the 6 parameters, of which that graphic that I showed, that chart, that is, what I think that any creationist must explain how it is that we were able to so accurately predict that chart. The 6 parameters that chart is based off of are not the 6 that you were giving me.
Okay, let's clarify something real quick. If I grant you, for the sake of argument, we're talking about 2 different sets of 6 parameters that explain the cosmos. As big of a stretch as that sounds, if I grant that to you, my biggest issue in that list of 6 things was that, let me see if I can find this over here, was basically the cosmological constant. And that is one of your original 6.
Yeah, we can talk about that. That is relating to dark energy, or at least dark energy is one potential explanation for the cosmological constant. There are others other than dark energy.
Okay, fair enough. But
essentially, what the cosmological constant is describing is the reason why the universe is accelerating in its present day expansion. That's all it's trying to describe.
Okay. I understand that, what the cosmological constant is there for. Whenever I identified it through basically open internet sources, that it is called the biggest blunder in physics. The reason it's called that is because the original cosmological constant was given by Einstein, and it was a really, really, really small value compared to what's accepted today.
So, okay, wait, let me clarify something there. The reason why Einstein said that the cosmological constant was his biggest blunder of his career was because when Einstein introduced this term into his equations, the reason why he was introducing it was because if you don't have this term, all of the matter in the universe just causes the universe to shrink and just like implode on itself like this. And so you need something else to balance it. And Einstein thought the universe was not expanding at this point. He thought we were in a steady state universe that's not changing in size. So he said, wait, my equations are showing that all the mass would cause the universe to shrink. So he introduced this cosmological constant to balance that out and say it's in a perfectly steady state. It's not getting bigger. It's not getting smaller. And then after talking with Edwin Hubble, Einstein realized, hey, wait a minute, the data shows that the universe is expanding. So then he got rid of the cosmological constant and basically said the universe is expanding, but the mass is causing it to slow down. And eventually it'll slow down so much that it'll start shrinking and it'll no longer be expanding. So he got rid of it, said it was his biggest blunder of his career. And it was only brought back at like the end of the 20th century when we made the observation, the actual observation of real data that showed us that the universe is not slowing down in its expansion. It's actually accelerating. It's expanding faster and faster and faster. So we needed to reintroduce the cosmological constant into the equations in order to model what we were actually seeing in the real world.
Okay. I want to point out that I already said basically the gist of that in my presentation. Einstein, he called it his biggest blunder because he just assumed without basically going against consensus at the time, exactly what you said and what I already said, that everybody at that time thought that the universe was static. And later it was believed that the universe was expanding, and so a different cosmological constant was evoked. And then later, after it was determined that no, it's not just expanding, it's accelerating, yet another version of it.
So no, you're just a little bit inaccurate in that middle phase. There was no cosmological constant in the middle part of that. They got rid of the cosmological constant. Einstein said it was his biggest blunder because, hey, the universe is not in a steady state. The data showed him that it was expanding. Hubble showed him the data that it was expanding. And he got rid of the cosmological constant. And for most of the 20th century, we did not have the cosmological constant in our models. We didn't have it. It wasn't in the terms. It was only after we found that the expansion was accelerating that it was reintroduced.
All of that to basically say, is my screen still showing?
Yeah.
Okay. Theoretical value obtained through the quantum field is nowhere near the value obtained from the study of type 1a supernovae and the CMB. In fact, it diverges by as much as 10 to the 121st.
That's a completely different point than what we were just on. And we talked about this already. This is known as the vacuum catastrophe or the cosmological constant problem. And as I already explained, the entire faulty assumptions that lead you to making that terrible prediction using quantum mechanics and lambda CDM is the fact that you're assuming that vacuum fluctuations gravitate, which is not a valid assumption to make. If you don't assume that, you don't get those results that you're saying are this huge blunder.
That's not, and that brings me to this point here. So I'm going to come back here and I'm going to go ahead and use this because it kind of puts it on screen a little bit better, even though I can't magnify it the same way. It is chosen. It is chosen to make things come out right. This is why the Big Bang Theory cannot be argued to explain microwave background or to explain a cosmic helium value close to essentially 25%. If you really believe in a Big Bang, you can choose parameters which will make observation and theory agree, but the argument is not based on basic theory.
Okay.
There's a little bit more. The emphasis was in the original. Okay. And he goes on to say, however, according to Paul Steinhardt, Albert Einstein professor in science at Princeton University, inflation is very flexible and can be adjusted to give any result. Any outcome is possible. Hence, he says it's not possible to find evidence to support or refute inflation. Which I think is,
I have a feeling that that's probably a quote mine. I would like to see the full context for that Paul Steinhardt quote, because you actually can, like, inflation has made testable, falsifiable predictions of like adiabatic heat transfer processes in the CMB that were then later corroborated and matched the inflation prediction. So again, that's a testable, observable, repeatable observation, that a prediction made by the inflation specifically, not just the Big Bang, but inflation specifically. And
here's the full source.
Okay, send that in the private chat if you could. But the point I wanted to make here was that earlier in your presentation and just now you claimed that these are just free parameters. And basically what's going on is that these scientists are kind of picking the values of these parameters that yield the results that they want that match like the actual observations. And that's what you're saying. That would explain how they were able to make that theoretical prediction that exactly matched the real world data, like bump for bump and valley for valley. But that fails as an explanation because each one of those parameters is not just a free parameter that you can pick any value for. When you actually look at it, they are constrained
That is not
by
what
other observations.
That is not what I said. That is not what I said. I'm not saying all 6 of them are free parameters. I'm saying specifically the cosmological constant is a free parameter. But here's the list again. We can say which ones. The gravity constant is not a free parameter. 3 dimensions is not a free
but those are not the 6 variables.
Are you telling me that this one here, the rest energy, the massive rest mass energy is not one of the parameters?
No. It's literally like you have like okay. So Hubble's constant in 1, that's just the expansion rate, kilometers per second per megaparsec of expansion. That's what that value is. That's one of them. You have the total energy density of matter. You have the total energy density of dark energy, or the cosmological constant. That is one, and that is not a free parameter. That is measured. The Dark Energy Survey did that. The Dark Energy Spectroscopic Instrument did that. We measure the value of this cosmological constant, like actually like sending up instruments to get a measure of them. Like these are bounded by real world observations. You can't just choose whatever number makes the math work out. You have to go by what value is measured.
Let me answer that real quick. It is true that you can take measurements and come up with a cosmological constant lambda. Yes, it is true you can derive it from measurements. It's still a free parameter because you can also pick other measurements to come up with a cosmological constant. And they don't agree with each other. And so what I did was I went to there's this website called physicsworld.com. There is a paper titled "A New Generation Takes on the Cosmological Constant," and basically what they do is they go through and the authors that are discussed here basically tell you plainly that they're looking for alternatives to the cosmological, to calculate the cosmological constant, because it is a free parameter. Yes, you can measure something and get a number, but you can also measure other things and get a different number.
Okay,
and
let me address that.
It's like,
let me just address that with a screen share here. Yeah, perfect. So this is how it's actually done. Like this is straight up from one of the cosmology papers that's working on this exact area. This is exactly what we're talking about. So this is showing that when you're saying it's a free parameter, that's not the case. So each one of these colors here represents a different measurement. So, and these are the different parameters, right? These are actually 2 of the parameters that are 2 of the 6. This is the energy density for dark energy, and down here is the energy density for matter. So you see here that there's a relation between these 2, and that's what's plotted in this graph. So these are 3 different, completely independent lines of measuring these things. One is the CMB. We talked about that. So these are all the measurements from the CMB in orange. And you can see here that they constrain what values that these 2 parameters can take. But you can see that there are different combinations that could work. Like over here, you could have 0.8 for this one, and then the CMB would tell you you'd have to have somewhere around 0.4 for the other. So you can see that it is constrained. You just can't pick anything. It has to be somewhere in the orange. But then you use another method like BAO, baryon acoustic oscillations, and that tells you it's got to be somewhere in the green. And then over here, you use supernovas in the blue, and then the real combination is where all of these overlap. So this is the freedom that you have to pick these parameters, is only in this tiny little zone right here. You see it's constrained by the real world measurements. They're not just free to pick any values. They can only pick values that are in this tiny little area. These are the only values that you can work. They're not free parameters, they're constrained parameters.
Okay, let me respond to that. I'm going to read you one of the deals that this particular physicist and his colleagues were working on. It says, lambda, as it is currently considered, only accounts for the universe's expansion once matter began to form structures, an era that lasted from 47,000 years to 9.8 billion years after the Big Bang. Garcia wanted to consider a form of dark energy that began to play a role in the earlier radiation-dominated epoch from the earliest moments of cosmic inflation. Inflation, the sudden and very rapid expansion of the early universe, is thought to have taken place some 10 to the minus 30 seconds after the Big Bang, but this rapid expansion is thought to have been driven by quantum fluctuations and not dark energy. So you didn't even want to argue this dark energy thing, and here they're saying that it had nothing to do with the initial conditions and the early continuation of the Big Bang.
I mean, that's obviously
for that reason. For that reason, it is a free parameter because you apply it to the portion you think it best fits.
Nope, that's just not how this happens. Again, in the consensus for cosmology, right, we're currently in the dark energy dominant phase of the universe. But before that was matter dominant, where dark energy didn't really matter for the universe's overall dynamics. The total amount of matter, the total amount of mass was what was important. And before then, the universe was radiation dominant. So the mass didn't matter. The dark energy didn't matter. The universe's dynamics were determined by its radiation components. So the universe goes through these different phases of radiation dominance, dark energy dominance, and different factors are important at different times. That's literally like the mathematics necessitates that it is that way. Like we could break down which equations these are coming from. It basically goes down to the fact that you have the certain constant in the equation to the third power versus to the fourth power. Like, and this is determined based on the actual observed dynamics of these entities. So this is necessitated by the mathematics itself. This is where this is coming from, and this is why we know, hey, dark energy is relevant for now. Radiation was relevant then. That's what's determining the universe's dynamics. So this all falls out of the mathematical structure of cosmology at this point. So this is not just a free parameter where you can just all of a sudden just insert it at whatever value you need it to be here. Like, that's not how any of this is done.
So to further make my point that this is literally, you get to pick certain pieces of the equation. A couple things to point out is that in general relativity, so Einstein comes up with his first version of the cosmological constant. So essentially what he's developing is a special relativity by adding in a cosmological constant. There are many special relativities. Here's the problem with the mathematical version of this that you're endorsing, is that you can come up with mathematical solutions to relativity and other types of mathematical models. You can come up with solutions to mathematical models that don't actually represent reality. They literally have no physical counterpart. Just because you can solve an equation and get a value does not mean that it has a physical representation.
I agree.
So what do we do to vet out this thing about the early conditions of this alleged Big Bang necessarily yielding what we have today?
I'll tell you what we do. I'll tell you what we do there, T-Rock. So, for example, with like the value for the cosmological constant, right? So in 1997, when we observed using supernova observations that the universe is accelerating in its expansion, we were able to use that data from supernova to calculate a value for the cosmological constant. And then we go over to like the CMB or BAO or some different other type, an independent means of measuring a value for the cosmological constant. And we get the same value using two independent means of measurement. So if it really is the case that we're just trying to, let's pick whatever number makes our observations work for supernovas, and we pick that number. And then we say, hey, wait a minute. When we go and we make multiple other measurements of other things that have nothing to do with supernovas, we get the exact same value for the cosmological constant. That's either a huge coincidence and we're just making these accurate predictions just because we just happen to luck out. We made this made up math that doesn't represent reality, but it gives you accurate predictions all the time that match with different independent areas of measurement. I mean, come on, it just boggles the mind that it could just be a coincidence.
Okay, so let me respond to all that. What you said was that you measure them by two independent methods, and that is literally the opposite of what this one quote that came from Physics World said. The theoretical value obtained through quantum field theory, aka QFT, is nowhere near the value obtained from the study of type 1a supernova and the CMB.
Because it's incorrect.
It diverges by as much as
because it relies on a faulty assumption.
You're saying what they
went through that three times now. We've been through that it is a faulty assumption that leads you to an incorrect answer, and it can be shown where the faulty assumption is in the math, and it's not valid. We've been over this 3 times now.
So clarify real quick, because you haven't actually talked about this specific thing, quantum field theory.
Yes, I did talk about this. Remember how I said that the assumption in question is whether or not the vacuum energy gravitates.
You are quantum field theory. What you're saying is that quantum field theory is incorrect.
No, I'm saying that using QFT to make this prediction is an incorrect application of QFT, and that's what most physicists will tell you. I have spoken about this exact subject with several physicists. The vacuum catastrophe and the cosmological constant problem are really points of interest to me. And I've had these conversations, and they have broken down in the math why it is incorrect to use QFT to make this prediction and why that is incorrect because of the faulty assumptions in that process. And I've highlighted that for you 3 times now. You cannot use QFT to make a prediction about the cosmological constant.
So you're saying it with authority as if it's absolute fact, but can you be a little more specific? Because if I'm remembering correctly, quantum field theory, what they're actually doing, what'd you call it, the crisis, the vacuum crisis?
The vacuum catastrophe.
The vacuum catastrophe. Okay, so essentially quantum field theory, what it's doing is trying to say, okay, every particle in the observable universe contributes something to that vacuum. So you calculate a value and then you find out it does not match.
No, what you're assuming is that virtual particles in vacuum fluctuations gravitate, which there's no evidence to suggest. And you're just having to make a claim that's completely unsupported by any evidence or anything that we know about physics. Like literally, there's no reason to assume that vacuum energy, these quantum fluctuations in the vacuum, gravitate. They're virtual particles. They're not real particles.
So I would agree there's no reason to follow quantum field theory. That's not really my point. My greater point is you have a discrepancy between this and what's calculated from type 1 supernova, type 1a supernova and CMB. But
and my point is that these calculations are incorrect. This is well trodden. This is the 4th time we've been over this now, T-Rock. I don't know if you're just refusing to acknowledge the point that I've been making. Maybe if you could steel man what I've been telling you this whole time, I would feel better that you've actually heard my point.
I've already reiterated your point. Your point is that you have 2 different methods independent of each other to measure this the cosmological constant, and they both yield the same value.
It's not what we're talking about right now, is it?
Yeah, that's what you said. That's what you said. The cosmological constant is not a free parameter because it's calculated from 2 independent methods.
And this is not a measurement. These QFT numbers, this is not a measurement. Nobody has observed the vacuum gravitating. If somebody makes an observation of how much the vacuum gravitates and then uses that to calculate the cosmological constant, then you'd have something. But this is not that. This is you like saying that people are making mistakes in how they are applying QFT, and they are inherently putting in assumptions that are unjustified in their calculations and making a leap of logic that is not substantiated, and they're making a faulty prediction because of that. That's what you're arguing. That's all the point you're making.
I don't want to spend too much time kind of re-saying the same thing over and over.
And let's not.
I've already acknowledged. I know what your position is. What I will say, though, is backing up to what I was trying to say a while ago about how do you flesh this out? How do you know the early phases of the Big Bang produce what we see today ultimately? And you're saying, well, you have to step through all this different math for these different scenarios and so forth. Donnie, are you sharing my screen?
Yes, now I am. You're good.
Okay, you can see everything. So what I have here in column A are several, but not even all of the problems with some of the tenets or assumptions behind the Big Bang in terms of either of what it should do. There's the baryon problem. That has to do with matter and antimatter. There's the quantized CMB problem. It appears to be quantized in discrete packets that are literally more or less centered around our solar system or the Earth, however you want to say it. But it's quantized, and it's not a prediction of Big Bang theory.
It's just not true, though.
There's inflation. What in the world is inflation, and how do you demonstrate that to anybody? I mean, you've described it. You gave a nice little graphic there about it, but how do you actually demonstrate that to make it valid science theory?
You remember how we already went over that? You remember how we already went over that, where I said that inflation makes a specific prediction about adiabatic heat transfers in the CMB that was then later observed and tested and verified? Remember that part?
We'll get to that in a minute.
Okay.
There's the singularity problem.
Are we going to go over all 17 of these?
I'm just reading them off. I'm not going to go into a long diatribe or anything. I just want to point out there's a singularity problem in terms of the quantum fluctuation.
There's not, though. I don't acknowledge these as problems so far.
Okay. Early, there's a problem with early formation of galaxies. There's a problem of the expansion of space, not actually.
Okay, wait. You can't just keep going through these and then not allow me to respond to any of them, right? Like, the early formation.
Well, let me go through the list for everybody's sake, and
you
then
want to go through 17 of them where I can't say anything. And you want me to respond to all 17?
I've got them on the screen. I'm just reading them off so that people listening can
let's go one by
one
at least.
Did you guys want to do one topic or one point at a time? Maybe T-Rock pick one or two and then cover them.
I'll start at the top with the baryon problem.
Okay, well, first of all, that's not even how you spell baryon. So please, what is the baryon problem? It's a Y, not an I.
Thank you. That doesn't actually endorse the Big Bang, though.
So what's the baryon problem? Why don't you lay it on?
Baryon problem is that in the what you kind of talked about this quantum physics experiments that demonstrate that quantum fluctuations are real, and I said, well, you're equivocating because what's done in a lab is not remotely similar to what happens in the hypothetical scenario of the Big Bang. The baryon problem is that you should get equal amounts of matter and antimatter when you convert pure energy into solid matter or particle matter.
Yeah, just the matter antimatter discrepancy. Sure.
Mm-hmm.
Yep, that is an unsolved problem.
Yep. And so I believe
when you actually do bring up an actual legitimate unsolved problem, I have no issue acknowledging that. I'm not saying there's no problems. I'm just saying I don't think quantized CMB or inflation are the problems you're making them out to be.
Okay, now the baryon problem. So the deal here, of course, is that the Big Bang explicitly should predict equal amounts, and that's not what we see. So observation does not match quote unquote theory at that point. There's the quantized CMB. You don't seem to like that, but
I don't think that it exists.
You don't think it exists?
No, I don't know where you got it from. I think maybe you're thinking of like the axis of evil or something instead of I don't know what quantized CMB even is, T-Rock. I don't know what you're trying to describe there. But if you're talking about like the axis of evil or whatever, which is like the little fun pop science name that they gave for this little axis that goes through the lower like the multipodes of the CMB, like that I showed, like it only very roughly corresponds with the axis of the solar system. It's not exact. It's only like if you're just squinting your eyes at it, and it's only for the lower multipodes, which are like have the largest error bars and are the most prone to error, just like structurally with how they're calculated. You can't get rid of that error.
So what it alludes to?
I'm saying it's not real.
What it alludes to, though, is that there is a larger scale structure to the universe that the Big Bang does not predict. As a matter of fact, it predicts the opposite. Okay,
what now? Are you back to the opposite?
Well, I'm just making a general observation that the Big Bang idea predicts a relative lack of structure in the universe, but there is a it does. It's supposed to be, and we'll get to that down here. We can jump straight to it if you want to.
Just FYI, an entire unit of my cosmology course was large scale structure formation. It is absolutely predicted by the Big Bang model.
No, it's ad hoc to the Big Bang model.
It's not.
The modern synthesis of it incorporates it, but only because it has to. Okay, so then there's the smoothness of the CMB. Now, this is one that whenever the relative uniform temperature across the sphere that the map is demonstrating, when that was first discovered, it was a surprise to physicists. They were not expecting it because that is not what the Big Bang
inflation solved
predicted.
that problem, as well as the horizon problem solved by inflation. Although there are alternative solutions to both of those problems that just have a thermodynamic necessity towards smoothness.
So now you're invoking one of the most untestable, unobservable portions of the Big Bang.
Remember how twice now I've given you an observable, testable prediction that was verified of inflation? Remember that? Observable, testable, repeatable science?
No, it's obviously circular reasoning here. You've got
it's
smoothness.
It's scientific method, T-Rock. It's not circular reasoning.
Yes, it's circular reasoning because you've got a smoothness to the CMB. So you basically come up with a mathematical model to describe it and then go, see, I've proved inflation is responsible for it.
That's not what's happening here. Let me just break this down, right? The scientific method you start with an observation. You observe the smoothness of the CMB. That leads you to develop a hypothesis. Maybe inflation happened, and that's what caused this smoothness. And you use the mathematics of your hypothetical model of inflation to then make a prediction that doesn't have to do with the smoothness of the CMB. So you say, well, wait a minute. If inflation happened, maybe we should see evidence for adiabatic heat transfer processes in the CMB. That would be a prediction that inflation made. And then we go and look, and we find them. So this is the scientific method. This is not circular reasoning.
But inflation does not predict that. Inflation basically predicts that you go through a period of rapid expansion, and then all of a sudden you have some undescribed deceleration of that it essentially stops completely.
It's not undescribed.
It's not
there's a mathematically rigorous explanation for that, as like the inflaton field gives way to like particles and the fields of nowadays when you have like symmetry breaking. Like this is a mathematically rigorous explanation. It's not just hand waving and magic. You can use it to make testable predictions. That's what science does.
It's post hoc math that's basically forced to fit the data after the fact, because the Big Bang was originally conceived and inflation was originally conceived long before there was any data. Okay. In other words, people were just guessing at it. And then after you start measuring and observing the characteristics that we actually have tangible to us today, you literally can reconstruct your equations to make it look like that it fits that idea. It's like hocus pocus to me, because I described earlier how you can have a mathematical solution that doesn't represent physical reality. Well, the other side of that coin in terms of good science is you can have a mathematical solution that does represent or can represent reality, but doesn't necessarily represent the actual course of events. It's kind of like you can mathematically model just about anything you want. Like, let's say a ball rolling down a ramp, you can come up with a mathematical set of equations that describe how it got from the top of the ramp to its final resting place. That doesn't mean that's the path it actually took.
Yeah, so I would just challenge you, T-Rock, to come up with a mathematical, and maybe use some numerical methods to derive a model that can show you the exact chart. It makes the same prediction as the Big Bang model for that exact same power spectrum chart that I showed in the beginning. Show me the mathematical model. Use however many free parameters you like, and we'll see if your model using that math can make any testable, falsifiable predictions. And then guess what? You would be doing science. We would try to disprove your model. And if we couldn't, and if time and time again, every attempt to disprove your model failed, and you make predictions using your model that we then look and test and verify that your predictions are accurate, guess what? Your model graduates to a theory. And that's how science is done. That's how the Big Bang has gone through those hurdles. People have tried to disprove it, and the measurements keep coming out in the Big Bang's favor. And I think that if you were to make such a model, you would not be able to do it with only 6 parameters. If you were just to numerically fit that graph, it would take a lot more free parameters than just those 6. And those 6 parameters have such intricate mathematical relationships between them that are all testable and have been verified in the real world.
Okay, so real quick, all I'm going to say about that is all of these physicists that are looking for alternatives, they're not creationist. They are looking for alternatives because they recognize the problems that I'm pointing out. And they're not just hand waving them away by saying, oh, we have a slick mathematical model that tells us everything we need to know. We can stop now. No, they recognize the problems. That's why this stuff is out there. So moving on, horizon problem. It's very closely related to the smoothness of the CMB.
Inflation,
It's basically the idea that the opposite sides of the universe have not been in thermal contact with each other in order to even out the temperature the way it is. It's called the horizon problem, and inflation is thrown at it. Actually, a modified version of inflation.
You mean?
No, it doesn't solve it. What it does is it attempts to make an explanation for it. But the idea is that, okay, the inflation, basically you have a period where everything stayed close enough together to thermally equilibrate. And then we get the current epoch of expansion afterwards. So inflation has come to an end at that point. It hypothetically solves this problem. It doesn't really, because again, demonstrate inflation to me. You described what you think it is with a graphic. You talked about it and you said what the idea behind it is, but nobody can ever demonstrate inflation.
What about the freaking, for the 4th time, T-Rock, when you say stuff like this, please address what I have actually said tonight 3 times now about the testable, verifiable, falsifiable prediction made by the inflation model that was then observed, tested, repeated, and verified. Address that.
I did. You kind of breezed over it and said, no, it doesn't matter. We have the numbers we want. We're done. What I said was that when you construct your mathematical models, you do have free parameters in them, and you can construct mathematical models that appear to solve one problem, but they don't necessarily solve another. And you can construct mathematical models that don't represent physical reality, and you can construct mathematical models that could hypothetically have a physical rendering to them, but don't actually describe what really happened.
What about a historical example of this from another point in time in history? Can you think of any other time where we've constructed a scientific model that made precise, accurate predictions time and time again, where we're predicting this should be a certain value. This chart that we observe should be a certain shape. We're making precise predictions, and we keep getting the right predictions, but then it's not true, and the whole thing was false. Like,
maybe you're alluding to planetary motion in our solar system as an example.
no, I'm just asking you because, like, I mean, I
yeah,
guess
I mean, that's
Newtonian physics made a whole lot of accurate predictions, and it still does. It's like correct.
so. Yeah, Newtonian physics actually works right here on terra firma, but it starts to fall apart the further you get away from Earth, and needs relativity to clean up some of its inaccuracies. Right. But as I pointed out in my presentation, once you get beyond our solar system and start looking at distant galaxies, you actually need more than relativity. So even relativity doesn't solve all the problems.
Yeah. I mean, so I don't know what I don't understand how what you just said is relevant here, but the point I'm making is that the math we have now is making accurate predictions. We predicted we should observe adiabatic heat transfers in the CMB. We did. We predicted that the CMB power spectrum should have this exact shape that it did. Like, this cannot just be coincidence.
Actually, yeah, let's go back to that real quick. You're referring to your graph that you used in your 7-minute video?
Yeah, I'll pull it up.
Sure.
Can you stop your screen share so I can... Okay. Can you see my screen?
Yep.
Okay. This is the graph that you're talking about.
Yep.
Or we're talking about, rather.
So we can talk about this for a little bit, because you've got L equals 2 as the starting point. And in your commentary, you said it goes up to something like L equals 1500 or something like that.
Here it's going up to 2500.
2500. Okay. So in other words, there's a rather large range, and you're only giving a representative sample up to 100.
Yeah. And I can talk to you why we get rid of the first L value if you want, but
yeah, go ahead. That's kind of what I'm actually interested in.
The first L value you get rid of because it essentially is just reflection of the Earth's motion. So as the Earth revolves around the sun, you get a mix of red shift and blue shift as you're moving closer and farther away with the Earth's motion. So that first L value is just reflective of the Earth's motion. All you see is the red shift and blue shift over the course of the year as the Earth goes around the sun. So you get rid of that you subtract that from your results, because like that's where Earth's movement shows up.
So this is called the multipole moment.
Yes.
And what you're alluding to, that first L equals 1 value that you get rid of, that would be what we would call the monopole.
Dipole.
Huh?
The dipole.
Why would it have an L equals 1 if it's a dipole?
That's just that's the nomenclature behind it. I don't know.
Okay. What I'm getting at is there is actually a monopole problem with the Big Bang idea. And that is that we should see monopoles because of this expansion.
You talking about like magnetic monopoles?
No, they're just called monopoles. I'm assuming they're just referring to a general electrostatic charge. But it's called the monopole problem because the Big Bang predicts essentially that the one you described, L equals 1, is actually the dipole. What it describes is the Big Bang predicts that these should be stretched out so far that you should be able to detect one end or the other of them, hence a monopole. Even though technically a monopole should not exist.
You're confusing two different things here. Like, we're talking about multipole moments, which is just a mathematical thing. Like any spherical pattern you can break down into different multipoles, just like you can break down a complex signal into different sine waves. But you're talking about magnetic monopoles, which is a totally different thing. Like, that's a physical object. The multipoles are not physical objects.
Hold on just a second.
Yeah, and again, I'm not aware of which math you're saying is used to predict magnetic monopoles, but I don't know much about magnetic monopoles where I would be able to get into that argument here, because it really doesn't have that much to do with this chart here. But yeah, so there's a few things that we haven't touched on yet. After we talk about this chart, there's you had brought up stuff about like dark matter and how that's not observable. We haven't talked about dark matter yet. And then there's the point I brought up about how really, really weird all the farthest galaxies are, and how there's no explanation for that without a Big Bang. So just want to touch on those before we wrap up. Are you there, T-Rock?
Yeah, you were cutting out real bad, and I couldn't hear a lot of what you said.
I think it might have been on T-Rock's end, because he cut out a little bit there for me too. But Grayson, if you'd like to reiterate what you said, we got about 15, 20 minutes left. So I like your idea, Grayson, where we make sure to leave no stone unturned and discuss all the relevant topics. And so how should we proceed now before we get to those last couple?
Okay, so the point I was making, T-Rock, was just that I don't think magnetic monopoles are relevant to the multipoles of this graphic. This graphic was my main, what I think is the strongest evidence that I don't think any Big Bang detractors could explain this chart. We've talked about it a little bit, but in the time we have left, I wanted to make sure that we got to talk about dark matter, because that was a point that you brought up, as well as the very farthest distance galaxies.
Okay. Yeah. So pick your.
So do you want to just go into dark matter now, or did you still want some stuff to say about this chart?
I've got a brief deal about dark matter. We can come back and talk about multipoles later, maybe. But I couldn't get my source to come up.
My point about dark matter is that it's observable. Like, we observe its effects multiple different ways. It's not unobservable.
I would like to put a big, strong qualifier on that. We can observe the effects of something happening. We cannot observe dark matter.
Well, that's how we observe things, T-Rock. In general, we observe the effects of things. We don't observe things directly. Like, when you look at something, you're just observing the effect that it had interacting with electromagnetic radiation. When you touch something, you're just interacting, like you're observing its effects from its electromagnetic
we get that. We get that. None of us were born yesterday.
The way that you're talking, it kind of makes it sound like you didn't get that.
No, that's you projecting on me.
Well, you said it's not observable. We only observe its effects, but now you're acknowledging that actually all observations are observations of effects. So
no, we observe an effect that's contrary to the predictions of the Big Bang. The effect we observe is that galaxies appear to be rotating faster than they should. Now,
why is that a prediction of the Big Bang?
Why is that a failed prediction of the Big Bang?
Why is that a prediction of the Big Bang at all?
Well, first of all, it's conservation of angular momentum.
So what does that have to do with the Big Bang?
So the Big Bang is supposed to hold conservation of angular momentum as a primary foundational part of the so-called theory.
And here's the thing, though, is that the Big Bang not being an explosion, like the actual generation of angular momentum is during the formation of like galaxies, planets, and things like that, and it depends on the actual process of their formation. None of that is the Big Bang. That's galaxy formation. That's planet formation. That's not the Big Bang.
That is a direct result of the earliest part of the Big Bang, where you transition from energy into the cooling down part and start forming particulate matter. And then you're supposed to, yes, that is the Big Bang.
No, formation of galaxies is not the Big Bang. Like, you can say,
the formation.
The dinner I had tonight is a result of the Big Bang. So
the formation of particles is the Big Bang direct connection.
Okay, so you're saying the formation of particles imparts angular momentum to galaxies?
That's not what I said. You keep projecting ideas that I did not say.
So then what are you saying about angular momentum?
So Big Bang, going back to the beginning, you've got this imaginary version of a quantum fluctuation that's kind of dropped somewhere in an undescribed position in this inflation cycle, and it's supposed to rapidly expand space so that energy and particles begin to appear further and further apart from each other, and then at some point, inflation hypothetically slows down and or comes to a complete stop, whether instantaneously or through some, time measurable deceleration. I don't know. You can comment on that. But then at that point, when you start cooling down, you start forming particles. This is all Big Bang cosmology. This is not quote unquote formation of galaxies and stars and stuff pushed off outside of the boundaries of the deal.
I would agree what you've gone over so far as part of the Big Bang model. There you go.
Yeah. So what's supposed to happen from there, though, is you start getting these particles, and the original version, the unfalsifiable Big Bang, basically says that it's gravity that starts slowing inflation down. Now, personally, I find that extremely suspect and very unscientific, because on the one hand, space is supposed to basically defy all of the rest of physics in the sense that it can expand faster than the speed of light, but nothing, including energy, can move faster than the speed of light. But now all of a sudden, gravity is supposed to be responsible for slowing the expansion of space down. That I find that to be untestable, unfalsifiable, extremely unscientific. But the real point, though, is that you get to this point where you start forming particles, and through gravitational attraction, the particles start coming together to form actual solid matter at some point.
If you ignore all the initial conditions, yes.
And here is where you get angular momentum, because it's through this gravitational attraction of pulling things together that the idea is real simple, doesn't require a PhD to understand, but you've got particles coming into this system from random directions and inducing a spin to it.
Yep.
So I'm back to where I was a little while ago. Angular momentum is a prediction of the Big Bang, but galaxies don't seem to be following the conservation of angular momentum.
So this whole point was just that if you assume there's no such thing as dark matter, then you're saying that the conservation of angular momentum is broken. But if you have dark matter, then it's not.
No, I didn't say
so
that.
So does having dark matter fix what you're talking about?
What I'm really alluding to, no, it's just a wordiology thrown at a problem.
What does that even mean?
Wordiology? You're just throwing words. When you say dark matter, it literally is invoked to explain the rapid rotation of galaxies, but you're just throwing a word at it without actually knowing whether it exists or what it is.
No, I'm not doing that, actually. I think you might be projecting now, but I'll unpack what I'm saying here, right? Because the rotation of galaxies is what initially caused scientists to say, hey, it looks like there might be this dark matter that's causing these galaxies to rotate this quickly. Has nothing to do with the Big Bang. Again, like the fact that galaxies rotate faster than is predicted in a universe without dark matter doesn't have anything to do with the Big Bang. The universe could be in a completely steady state and just be eternal into the past, never changing in size. Galaxies would still be rotating too fast. Has nothing to do with the Big Bang. But that is the first line of evidence that led people to hypothesize the existence of dark matter. Since then, we have like a dozen other independent lines of evidence that all independently corroborate the same amount of dark matter in the universe. Like literally, you can look at the CMB, you can get a number for dark matter there. It's the same number of dark matter, the same amount that you get when you look at the galaxies, the same number you get when you look at galactic merger. It's like the bullet cluster that modified Newtonian gravity completely fails on its face to even say anything about. You can look at literally, I could go through maybe 6 or 7 different independent means of all observing the effects of dark matter, and all of them tell you this: there's the same amount of dark matter through all of those independent measurements. You're measuring
the very existence of dark matter is being contested in the scientific community right now. The very existence. I'm not making this up. I am not just a creationist.
Look, there are physicists that are like modified gravity people or modified Newtonian dynamics people, the Mond people. You point out like actual movements, but there's a reason why those movements are so fringe and why they're dying off so quickly in recent years. It's because we keep getting data that rules them out. Like we had the wide binary system data that came out last year in 2023 that literally like falsified modified Newtonian dynamics by a factor of like sigma 16. It was insane how hard it got falsified by the data. Like the differences between dark matter and these other ideas is that dark matter can explain all the observations we have way better than any alternative. If somebody comes up with an alternative model that can explain stuff like the bullet cluster better than dark matter, sure, go for it. But right now, it's literally the best explanation.
Let me respond to all that real quick. So you referenced 16 sigma and collection of data and blah blah blah. So the collection of data is not even remotely complete yet. Sure. There's still a healthy amount of data being collected by JWST specifically to answer questions that are not answered by dark matter. So it's not like, okay, it's the best thing going, we don't need another replacement. It's more like there's still something really weird going on out there and we need more data to try and explain it. It's not as explained as you're making it sound. The 16 sigma thing, actually, I watched, and anybody can go watch Sabine Hossenfelder's video on this. Basically what she describes is you pretty much have to favor a specific subset of data to come up with that 16 sigma idea. Meanwhile, the Mond model, the reason people are attracted to it at all is because when you apply it, you can literally get a better fit of galactic rotation than you can from dark energy models. Because you know, dark matter models, but you know, quote unquote, how much matter should be there by the excess rotational speed that it has. So you can just work the physics on that and go, oh, we're missing a bunch of so-called matter of some sort.
Yeah. So here's the issue. Here's the issue is that like when I could list out 7 things that dark matter can explain, and you say, hey, wait a minute, modified Newtonian dynamics can explain one of these 7 things better. But then when you really look at it, it doesn't really explain it better. And it still explains the data, but it's around the same explanatory power as dark matter. But then you look at the other things, and those things completely falsify modified Newtonian dynamics, like the bullet cluster. Impossible for modified Newtonian dynamics to explain. It literally just pokes a hole in the entire idea, rules it out entirely. Like if you just look at the total data that you have, instead of just myopically looking at galaxy rotations, you look at all of the things that dark matter explains. Nothing else can explain it like dark matter can. If there was an alternative, I would be saying it. I'm not saying I 100% just believe every hypothetical thing. Like I need evidence to support my ontology. And dark matter has corroborating lines of evidence from like a dozen different independent sources. It's not going to be touched in terms of the evidence.
So dark matter also does not explain galaxy clusters either, and which brings me to the next point.
It actually does.
We've got what's called the crisis in cosmology. It's called that for a reason. It's called that for a very specific reason, and it's because
the crisis of cosmology
the theory,
is real.
The so-called theory does not match the observation.
Well, no, I disagree with that. But let me just summarize this real quick. 2 things. So what was the first thing that you said? I've already lost it. You brought multiple points there. Anyways, the crisis of cosmology is just when you're using like the CMB, you get a value for the Hubble constant of like 67. When you're using supernovas, you get 70. Wow.
73 point something.
Yeah, it's around 70. Both of them are giving you around 70. Yes, I know that there's not a statistical overlap between them, and like there's a crisis there between those different measurements. But most physicists will say, yeah, the CMB data is probably correct. And when you look at other supernova data, not just the Cepheid like measurements, but when you look at measuring supernovas, with like JWST, Wendy Friedman just came out with this analysis a couple months ago. You do other measurements of supernova, guess what? Those are completely in line with the value that you get from CMB. And she could have potentially just resolved that crisis this year, just a couple months ago. The thing with that crisis in cosmology is that it's really new. Like it's like less than 10 years old, basically. So it's like a really new thing. I'm sure that in like, you know, the next decade or two, we'll probably have it resolved. But again, it is a current ongoing crisis in cosmology. I'm not saying it doesn't exist. There's not a statistical overlap. But at the end of the day, you're arguing between like 67 and 70. Like, come on.
No, you're saying the numbers are wrong. The actual value is roughly 67 to roughly 73, which means about 9% increase in the theoretical value coming from the observed measurements. So now you've got a dichotomy here. It's not 67 to 70. That would be what, like 5% or less. It's more like 9%. And basically in good science, you always prefer observation over the hypothesis or the quote unquote
that's
theory.
The point that I want to correct you on here, because this is not a conflict between theory and observation. This is a conflict between observation and observation. That's the crisis, is that when you make an observation with the CMB, you get a slightly different value than an observation with supernovas. It's comparing two different observations. It's not comparing theory and observation.
That's funny, because that's the exact opposite of what the physicists are describing it. They're describing it the way I'm saying it. They're saying it is literally
physicists, T-Rock.
They are literally saying it's the difference between what the theory predicts and what the observation demands.
Well, okay, I've learned about this from a cosmologist in the field. I think it's probably more likely that you're probably just not understanding what the physicists are saying than I'm incorrect on this, to be honest.
So I want to go to another technical point that kind of helps elucidate some of this. There is yet a third version of this. I don't know if you were aware of it or not, but there is a third version. Huh? No. A third version of the expansion rate.
There's several different measurements of it. I don't know which third version you're talking about. There's multiple. There's more than 3. There's CMB data, there's BAO data, there's like 3 different kinds of supernova observations that you can calculate H0 from. There's way more than 3 measurements of this.
Gentlemen, we just got a couple minutes left.
I did want to get to the point about the farthest distance galaxies.
Okay, we'll do that. I just want to point this one third measurement out real quick. It's called kilonova. There's a kilonova that's basically like a neutron star, sort of. But anyway, it's used to also calculate an expansion rate. And unfortunately for the astrophysicist, it creates a value kind of smack dab in the middle of the CMB version and the observed redshift version. And so you've got 3 different measurements that don't agree with each other. And hence, that is why there is a real crisis in cosmology, and the internet is just loaded with people talking about this, trying to come up with a solution, because it literally does not match the predictions that it's supposed to match.
Again, I think you're confusing 2 different observations with predictions observations there. But like, again, look at Wendy Friedman's work. She just published it a couple months ago. She showed that you can look at supernovas and they do actually agree with CMBs, just with different methods other than the Cepheid method that was the source. But it is a real crisis. I do think it will be resolved. Like, you know, it's a pretty recent crisis, just of like 2015-ish. And it'll probably be resolved here in the next few decades. I don't know what the resolution will be, but we're making strides. Wendy Friedman just this year made good strides and seems to have a potential resolution for the crisis. But yes, the biggest issues in cosmology now are: what are dark matter, what is dark energy, and how do you resolve this crisis that we're talking about here? These are like the big 3 current unsolved problems in cosmology. So that's what we've been talking about a little bit so far. Can we talk about the farthest galaxies now? Let me open up my let me just do my last screen share here just so that you can see the list of the different properties that we have observed that these really distant galaxies have. And like, again, the creationist prediction here that Dr. Lyle made was that JWST should observe these really redshifted galaxies to be essentially just like the galaxies that are close by us. They shouldn't be that different. So that was at least one creationist prediction for what we observe, and he's been completely falsified. So, like, yeah,
you want me to respond to that?
Yeah. I'd like your thoughts about why are these galaxies so weird? Why do they have the properties listed on the screen here?
They don't have all the properties listed on the screen, and not all the properties listed are directly relevant. So have the highest redshift. As far as I'm aware, Lyle and any other creationist physicist wouldn't have ever said anything different than that. Further,
no, I agree. I agree with that part. It's more so his prediction was about metallicity, and he predicted that they should look like modern galaxies.
I'll be honest with you. I don't have anything to say about very low metallicity other than what I said earlier, in that there is a whole lot of data yet to be collected. And so it's a little bit early to make that type of claim. But you're also talking about metallicity at the galaxy level. And where you really need to observe it at is at the star level. And there's not enough data there to do that.
You can get the spectra, like basically you're doing spectroscopy on this light, and you're determining what elemental composition it has. So it doesn't really matter. You're never going to get the resolution where you can do individual stars that are that far away. That's just not feasible.
Well, some brave scientist might figure out a way in the future. Who knows?
If we get really lucky, gravitational lensing maybe. But the fact is that we have done studies that have actually taken this data of the very most redshifted galaxies and looked at what, like, spectroscopically we can tell is there, and there's very low amounts of heavier elements. Like, I can send you a study where the highest that they ever found was about 1/3 the amount that our sun has.
Yeah. Okay. So at the galactic level, but
as far as galaxies.
Okay, so the number 3 are time dilated. Now, as little as I know about Einsteinian physics, that's a prediction I would make. So it can't be unique to Big Bang Theory or any opposing view.
Well, it shows us that the universe is expanding. That's what it shows us. The fact that they're literally moving in slow motion when you look really far, that shows us that there has been an expansion of space and time, and that the universe is currently expanding. So that's all. That's why I include that there.
Okay, I just want to point out that as time dilation goes, gravity also causes time dilation.
Yeah.
So there's more than one factor at play there. And it's not, again, it doesn't single out the Big Bang or any of its predictions.
Here's the issue with that, T-Rock, is that we're looking at the same objects. We're looking at supernova that, like, have the same amount of gravity, right? As a close one would have the same amount of gravity as a far one, because they're occurring at the same mass value. So they have the same gravity. These are like type 1A supernovas that are very certain conditions that lead to that always trigger at the same mass value. It's called the Chandrasekhar limit. Whenever they reach this mass value, they go supernova. So we know that this is the same amount of gravity involved for a close one versus a far away one. But we're watching the far away one happen in slow motion, and we're not watching the close one happen in slow motion.
Well, like I said, there's more than one factor at play, and gravity is not the only one. Actual distance is another one.
Only if space-time is expanding.
And speed is another one. The velocity is one of the things that invokes time dilation. And all of that. And we're back to the very beginning of the debate whenever I said the expansion of space is part of the typical creationist model. So it doesn't set the Big Bang apart in any way.
If you agree that the universe is currently expanding, then you must necessarily agree that it was in a smaller state in the past, which is what the Big Bang model is.
No, the Big Bang is a lot more specific than that, because in the creationist model, I think numerous creationists have pointed this out, not the least which is somebody like Dr. Kent Hovind, who's not a physicist, granted, but he is correct in this. The Bible points out many times, I believe as many as 17 times, that God stretches the heavens. And if you look at what it, yes, it is.
Every single one of those passages is stretched in the past tense.
Who told you that?
If you were reading the Bible to make a prediction, you would not predict that the universe is currently expanding, because the Bible explicitly tells you it's in the past tense that God stretched out the heavens.
Who told you that?
I've looked it up. I've looked at the Hebrew translations of the words. I wanted to make sure. Because every time I've ever seen it, it's in the past tense, stretched, not is currently stretching the heavens. You would not predict that the universe is currently expanding just from reading the Bible. And that's exactly why in 2,000 years of people reading the Bible, nobody ever once made the prediction that it was expanding. And that's why Hubble's results were so surprising to Christians everywhere on earth.
It is literally in the present tense in Isaiah chapter 40. Inhabitants thereof are as grasshoppers that stretch it. It's a semicolon, then the continuation of the original thought, that stretcheth out the heavens as a curtain and spreadeth them out as a tent to dwell in. Now, I've heard the argument you're talking about, and that hypothetically the Hebrew text is past tense, but I would disagree with that, because one of the strengths of the King James version is that it is considered to be one of the more accurate versions that came out.
Bro, you're disagreeing with the Hebrew original text for the favor of the English version? Is that what's happening?
No, to be clear, Grayson, to be perfectly clear, there are Hebrew scholars that also make other erroneous arguments about what the original Hebrew text supposedly means or says. And the point is that there are Hebrew scholars that disagree with those viewpoints. So it's not like all of Hebrew scholarship says the same thing on this point, because that's almost certainly not true. And so anyway, going back here.
Yeah, so how do you explain the weirdness of these galaxies? Like, they're really small, massive, and bright. They don't have the shapes of modern galaxies. They have high star production. What about that?
Number 5, extremely small, massive, and bright. That is actually, you can just do some basic YouTube searching, and you will find that that's not what a lot of the physicists are saying. They're saying some of these galaxies are way too big, and they're too fully formed. The expectation, as a matter of fact, there's a physicist named Michio Kaku, I think is his name.
Michio Kaku, yeah.
Kaku, sorry. Thank you. Anyway, basically what they're saying, this is one of the reasons that some physicists essentially want to double the age of the universe, because they're seeing these massive galaxies that look way too mature. They look way too fully formed. To be compatible with our current, quote unquote, current understanding of galaxy formation.
No, that is literally one guy. Nobody else is saying it other than this one guy that published a paper that said 26 billion years old. Everybody in the field made fun of him because it literally did not follow from what he was saying. It's literally one guy. It's like the fringe of the fringe, what you're describing. So when you say some physicists say this, like, come on, you're putting an incorrect idea into people's heads when you say that. It's literally one guy, one voice, and nobody else will back up what he's saying. So it starts with an R. I don't remember his name right now. But like literally, when you're also saying that people are saying these galaxies are too big, I think you're confusing the word massive for the word big. Because yes, massive can mean big, but in this context, they're saying massive as in has a lot of mass. They're saying it's really, really small, but has way more mass than would be expected for a galaxy that small. And that's because the universe was more dense in the past. And yes, I agree with you that the James Webb Space Telescope revolutionized our understanding of galaxy formation. It didn't change anything about the Big Bang. It showed us that, hey, galaxies formed a lot faster than expected. Again, has nothing to do with the Big Bang. The James Webb was not designed to test the Big Bang. It has not tested the Big Bang at all. It's designed to see infrared radiation. It's not designed to test the Big Bang.
Grayson, think logically about what you just said. It challenges, essentially what you said is it challenges our understanding of the formation of galaxies,
yep,
but not the Big Bang.
Exactly.
Except the Big Bang is supposed to be what caused the formation of galaxies. There is a direct transition from the end of what you're alluding to, the end of the Big Bang conversation to the formation of galaxies, and one necessarily has to cause the other. And if you don't know, if
that's like basically what you're doing right now, T-Rock, is you're confusing me for my dad. You're saying, well, listen, your dad had to cause you to exist. Therefore, you are the same person as your dad. That's what you're trying to do right now. It doesn't hold up logically.
No, Grayson, what I'm saying is if you don't understand the formation of galaxies, you may not understand what was supposedly happening at the final phases of this Big Bang epic that you're trying to cling to.
Okay, so if I didn't know who my dad was, does that mean I don't exist?
Grayson, you're literally jumping outside of the simple logic in how you understand formation of galaxies.
I'm making an analogy. What is not analogous about what I said?
What I'm saying is forget the analogy. Talk about the actual mechanics of how a galaxy is formed. It is supposed to be caused by the Big Bang. So the way you're trying to separate them in your analogy is completely erroneous, because you have to have a proper cause to understand the formation of galaxies. And if you don't understand the formation of galaxies, it directly alludes to you may not have the proper cause in the first place.
T-Rock, the dynamics that form galaxies are not the same as the dynamics of the Big Bang. Like the dynamics that form galaxies are mostly gravity and the dynamics of dark matter. Okay, the dynamics that form the universe is a different set of dynamics. When you're talking about the formation of the universe, you're talking about the Big Bang. And when you're talking about the formation of galaxies, you are not. It's not a difficult concept to understand. It's like if you were trying to analyze what caused a certain car accident, and you said, well, I could not possibly understand who was at fault for this car accident because I don't have the manufacturing information or the warranties for the cars involved. If I don't know when and where these cars were manufactured, how could I possibly know who caused the car accident?
False analogy.
What is false about it?
Because you're missing the direct connection between the end of the alleged Big Bang epic that started the possibility for galaxy formation to happen. And star formation, for that matter, both of them. It's like there is literally not a known physical mechanism to create stars in the vacuum of space.
Gravity. It's called gravity.
No, that's one of the major problems with the Big Bang theory. Gravity is the weakest of the major known forces by a long shot. Or by a long shot. What are you calling
small scales?
What are you talking about? What are you calling a small scale?
At the size at which the strong force is a stronger force than gravity is only at the size of like an atom. Gravity is a much stronger force than the strong force when you're talking about the size of a freaking galaxy. The strong force is not going to be forming a galaxy. Gravity is. This is not an issue. If you actually understand how gravity works, it's very obvious how gravity forms galaxies.
No, it's not. That's why they have these ideas called modified Newtonian dynamics and modified gravity.
No, that's not why they have those ideas.
Because it's not obvious.
T-Rock, actually, those ideas have nothing to do with galaxy formation. Mond does not explain galaxy formation. It does not even attempt to. It tries to explain galaxy rotation, not formation. There are no alternate theories of gravity for galaxy formation right now that have like anywhere outside of like fringe support.
The elephant in the room you're ignoring is that Mond is specific to large scales. It has, if it's a thing at all, it has to be relative very early in the universe.
And what I'm saying was that it was developed to explain galaxy rotation, and it doesn't even attempt to explain galaxy formation. It doesn't even attempt to.
It has to be there.
Okay.
And so the other big point, real quick, Grayson, you keep interrupting me and throwing these assertions out there. The big problem with the gravity that you just whizzed right past is that gravity is directly related to the radius of the volume of mass under consideration. Sure. And so as you increase the radius, you decrease the gravitational pull. So the real issue is not scale per se. The real issue is right here on testable terra firma, that it's mass density. If the mass density is not there, you can't have enough gravity to do anything.
I agree.
On larger scales, the whole idea of Mond being able to explain galactic rotation is that when you get into large scales, gravity actually becomes weaker, not stronger.
Yeah, well, I agree. That's pretty obvious. It follows the inverse square law with the radius. It's pretty obvious. Yeah. The thing is that you do have a lot of mass. These are massive objects. These are galaxies. And actually, the movement of galaxies beyond their rotation completely disproves Mond. Like literally, look at the way that the bullet cluster moves. Mond cannot explain that. In fact, Mond is falsified by the movement of those galaxies.
That's a galaxy cluster, correct?
The bullet cluster is two galaxies colliding.
Two galaxies colliding.
Yeah.
Okay.
And the way that they move during that collision rules out Mond as what would be governing their behavior. It has to be dark matter. At least that's the only explanation right now for the bullet cluster's movement.
The only explanation right now.
Yeah.
Okay. Sabine Hossenfelder is one of the primary ones that I listen to because she kind of gets.
But you don't even know how to pronounce her name. It's Sabina.
Sabina. Okay. Oh, so if I get logical fallacy alert, if I pronounce Sabina's name properly, therefore Grayson must be right about the Big Bang.
Well, if you're saying you listen to her all the time, you don't even know how her name is pronounced.
I'm pronouncing it the way it appears in English. In German, it's pronounced Sabina. Yes, I understand that. I've heard that before. I'm just kind of like a lot of people. I'm stuck in the English language here.
Okay.
We can move on.
Have you seen Sabina Hossenfelder address the bullet cluster? Because I have, and she says straight up that Mond doesn't explain it and that dark matter does.
Well, so the beginning about her is that she has waffled back and forth between these two ideas.
Yes.
For a very long time, apparently. She just keeps waffling back and forth. It depends on which data is presented and how the argument is presented. But her latest assessment that I'm aware of within just the past couple months is that she is now favoring Mond over dark matter. She still does not think it exists.
I don't think that she would go so far as to agree with you on that last point. But yes, she does waffle back and forth between these two things.
Her video title literally says that.
Yeah, it's a clickbait title.
Gentlemen.
Okay, so now physicists are clickbait artists.
Have we discussed all of the relevant topics to their fullness, do you think?
No, but we've been talking for a while, so we can move on.
Yeah, I mean, no, this has been great. This has been comprehensive and engaging. You both definitely know how to keep a discussion and a debate going and keeping it fun, entertaining. Now, did we want to do like a minute or two summary or just move right into audience questions? What do you guys prefer?
So do a quick summary.
Yeah, summary.
Okay, let's do a 2-minute summary, but it's been more informal than formal, so it's not extra strict. So this way we can wrap up our thoughts, wrap up our points, tie up any loose ends, anything that's been left hanging. Grayson, I guess we'll start with you. And go ahead. Feel free to provide a summary closing statement.
Yeah, so Sabina Hossenfelder might be a physicist on YouTube that waffles back and forth between Mond and dark matter, but at the end of the day, she still absolutely 100% acknowledges that the Big Bang did happen and that the evidence is sufficient for that case. In fact, everybody that T-Rock cited also acknowledges this. The evidence is multifaceted. It comes from things like galaxy movements. It comes from the CMB. It comes from the distinct little patterns in the CMB that I tried to talk about. Things like dark matter, dark energy, inflation, those are all secondary to the idea of the Big Bang happening because the Big Bang could have happened without any of these things, but they are part of our current consensus model of cosmology. So I thought it was worth talking about. There's numerous intersecting, cross-corroborating, independent lines of evidence for dark matter, dark energy, and inflation that all are corroborated within the lambda CDM model and the Big Bang. So basically, just to conclude, the weight of the evidence from multiple different avenues, but particularly from the cosmic microwave background, is pretty much proof beyond any shadow of a reasonable doubt for any rational person with a brain that doesn't have any preconceived biases and commitments to maybe another narrative, would conclude based on the evidence that it's pretty obvious that the Big Bang happened. And of course, it meets all the criteria of a reasonable scientific theory in that it's testable, observable, falsifiable, repeatable. It makes predictions that are all of those things, all of the good empirical qualities that make something a strong scientific theory. It makes predictions that fit all those categories. So I'll conclude with it there that absolutely the Big Bang is a reasonable scientific theory.
Thank you, Grayson, for that closing statement.